Okay, good afternoon. So this is our lecture number 33, and in the previous lecture we completed our discussion on the experimental methods. Now we will look into the computational techniques for multiphase flow. Okay. So at the moment, I pre-assume that most of you know about computational methods for solving fluid flow and heat transfer problems. But still, say if some of you don't have much idea, then in today's lecture I will just quickly discuss the very general concepts of the computational methods. Okay, so typically whenever we uses the computational methods for fluid flow and heat transfer, then one of the very popular term which you might have heard of is actually CFD. Okay, and if we just expand this, then we say it is nothing but computational fluid dynamics. Okay, so overall if you see, the term typically refers to the study of fluid dynamics only, but this word computational is just coming as some specific keyword with this fluid dynamics. Okay, so the major benefit of this keyword is that it is helping us to solve the fluid dynamics problems by using help of computers. Okay, or in more very generic sense, computational fluid dynamics can also be called as a branch of computational mechanics which is used for computer modeling or numerical modeling of fluid flow and heat transfer problems. Okay, so in very generic sense, like we say our fluid mechanics, okay, or in very generic sense, like we say our mechanics, okay, is the generic term. Then within the mechanics we say either solid mechanics or fluid mechanics, etc., are the specific keywords. In the similar way, computational methods are not only limited for fluid dynamics problems, but computational methods can be applied to any type of mechanics problems. Okay, so that's why the broad classification will be computational mechanics, and under the computational mechanics, if we are utilizing numerical modeling only for solving the fluid flow and heat transfer problems, then we will be calling it as computational fluid dynamics. Okay, so now can you tell me what is your understanding about computational fluid dynamics? What do you think what we do in CFD? Any generic idea? What we do in CFD? That is so. I have already clarified that, okay, the computational study or numerical modeling of fluid flow and heat transfer problems is CFD. But what is the process? What we do?
Develop mathematical models so that we can code it for computation.
Okay, so first say you are saying developing mathematical model. Okay, what else?
So that we can
Basically convert the partial differential equation into algebraic form by setting some boundary conditions.
Yes. So see, the primary concern is fluid dynamics itself is based on some governing equations which are actually governing the different physical phenomena which are happening in fluid flow and heat transfer. Okay, and these physical phenomena can be characterized by some equations which are called as governing equation. Okay, so for any fluid flow or heat transfer problem, particularly say whatever we are considering in our scope, we can pre-assume that almost all the phenomenon of fluid flow and heat transfer can be explained with the help of some mathematical equations which are called as governing equations. Okay, and from our experience of earlier knowledge, we know that typically the governing equations of fluid flow and heat transfer are in the form of partial differential equations. Okay, so this is something which we already know. So it means if we are considering the study of any fluid phenomenon, then the very first thing which we need to do is we need to define the governing equations. Okay, and we know that these governing equations are nothing but in the form of partial differential equations. Okay, that is first point. Now we are saying that we will be using computer to solve these equations. So computers do cannot solve partial differential equations. Okay, so what computer does? Computer can only do the algebraic operations and it can do only the logical comparisons. Okay, so these are the only operations which computer can do. So now, if I have to solve these equations which are defining any particular fluid phenomenon, if I have to solve these equations, then first I need to convert these equations to the form which is understood by the computers. Okay, so computers only understand algebraic equations. So it means these PDEs now I need to convert into algebraic equations. Okay, so that is the first part. So the process of conversion of partial differential equations into algebraic equations is something which is called as discretization. Okay, so this is called as discretization. So once you have converted your PDEs into algebraic equations, then your discretization is done. Now these algebraic equations can be understood by the computers. Now you can utilize the computer to solve this. So it means that in CFD, majority of the task actually we are only doing, because we have to tell the computer that okay, these are our algebraic set of equations, now solve these equations. So computer will be only coming into picture once we have converted equations into algebraic equations. Okay, so this is a very very important point. You should understand that computer can only come into picture once we are able to convert our partial differential equations into algebraic set of equations. Now, so in the course of computational fluid dynamics, we study different methods which allows us to convert partial differential equations into algebraic equations. Okay, so this is number one. So first we have taken governing equations and then say these governing equations we have converted into algebraic equations. Then what next we need to do? So governing equations for most of the physical phenomenon will be almost of the same type. Okay, so say if you talk about flow through a pipe, or if you consider say fluid is flowing in open channel, if you consider fluid is flowing over an aircraft. Okay, so for majority of these situations you will be finding there may be some scenario where one term is dominant over the other, but say in general if you consider almost if all the terms are coming into picture in your physical phenomenon, then for each and every type of flow problem, considering the specific nature of the fluid, specific nature means if you are considering Newtonian fluid or non-Newtonian fluid, then accordingly you will be finding that your governing equations are almost same. But these governing equations, we now need to define the physical phenomenon on which actually we want to apply these governing equations. Okay, so that is something which comes under the geometry creation, or we need to specify the geometry. Okay, we need to specify the domain where we want to solve the equations. And once I am specifying the physical domain, in that physical domain I also need to specify the boundary conditions. So whenever you have partial differential equations, if you simply solve partial differential equations to find their solution, you will be getting solution in the form of some unknown constants. And these unknown constants can be calculated by substitution of the appropriate boundary conditions. Okay, so boundary and initial conditions we need to define. So once you have defined your geometry, okay, so say if you are talking about flow through a pipe, you have defined that you have some cylindrical pipe and in this you want to study say flow. So you have to define that this is your inlet, this is your outlet, and this is your say some boundary which is not allowing your fluid to penetrate through that. So say I am defining it as some wall. Okay, now your computer don't know what is inlet, what is outlet, what is wall. So these are just the names which we know and we can correlate to the physical domain. Computer will be only talking in terms of the mathematical terms. Okay, so we need to specify these boundary conditions in mathematical form. Okay, we need to specify these boundary conditions in mathematical form. The meaning of mathematical form is you need to specify over here, say what are your field variables. So for majority of the fluid flow and heat transfer problems, you will be finding your field variables are velocity, pressure, temperature, etc. So you need to specify what is pressure at this point, what is velocity at this point, what is temperature at this phase, then what is velocity, pressure, temperature at the outlet. So likewise you need to precisely specify the mathematical conditions, then only your system will be actually able to understand. Okay, is this point clear? So this comes under the category of boundary conditions. After you have specified the boundary conditions, then you need to specify that, you also need to specify that what is your initial condition. Say if you are doing some transient simulation, transient simulation means time dependent simulation. Okay, so in that time dependent simulation, what will be happening? Of course solution will be evolving with time, but what is the solution at the initial point when the computations has started? That is something which you need to specify. So it means that within the entire domain you need to specify the values of velocity, pressure, temperature, etc. Okay. After this, one important point is we also need to specify the material and transport properties. Okay, you need to specify whether your fluid is air, whether your fluid is water, what is thermal conductivity for that, what is density for that, what is viscosity for that. Okay, so all these properties you need to specify. Fine. Once you have specified all these properties, then actually we go for the solution. So how solution is done? Once in your system you have converted your partial differential equations into algebraic equations and you have specified all the boundary and initial conditions, you will be ultimately getting nothing but a system of algebraic equations. You will be getting system of algebraic equations. Then you need to solve that system of algebraic equations. For example, majority of the time we use this discretization in such a way so that whatever the system of algebraic equations we are getting, this is nothing but a linear system of algebraic equations. So if we have linear system of algebraic equations, then we know that we have different methods, direct methods such as Gauss elimination method, okay, then iterative methods such as Gauss-Seidel method, Jacobi method, algebraic multigrid method, conjugate gradient method. So a large variety of methods are available for solving these linear system of equations. Once you have obtained this linear system of equations, you have solved these, then ultimately what we will be getting? We will be getting the values of all the field variables within the entire domain. Okay. Once you have the knowledge of all the field variables, then what you can do? You can plot the required set of parameters which you want to plot at different locations. Okay. I have intentionally left that. I will now discuss. So that is called as post-processing. Okay. So in the post-processing, what you will be plotting? Say you will be plotting some line plot, center line velocity as function of time, or velocity at the center of line. So position at central position, how velocity is varying, with radial position, how velocity is varying. So some line plots. You can plot contour of velocity. Okay. So you can plot different things like streamlines, path lines. So once you have the data, means once you have the knowledge of all the field variables, then you can plot any parameter what you want to plot. Okay, so it is not, you don't have restriction like experimental method where the instrument which you have mounted only you can measure, you can get the measurement of that particular quantity. Okay. In case of simulations, once you have solved the complete equation, you have now each and every variable known. Okay. So also, you also need not to change the location. For example, if you are doing experiment, if at a particular location in the pipe you are using your pitot tube, then you will get velocity only at that particular location. Okay, but once you are able to simultaneously solve the system of equations, you will be knowing value of velocity almost at each and every point within the domain. Okay, so that is the major advantage in terms of numerical simulation. You will be having solution known for all the parameters at each and every point. So by knowing that solution, actually you can calculate all the derived parameters. Okay, but now one important point I want to know. So when I am talking about partial differential equation, so partial differential equation is nothing but the solution of partial differential equation will be a continuous function. Okay, so if I solve a partial differential equation, say dy by dx is equal to something, then my y will become, say, f of x plus constant. Now I can substitute any value of x and everywhere I can calculate the value of y. So it means that will be giving me a continuous function. But this CFD will be giving me a discrete solution. Okay, so whatever the solution we obtain from CFD, that is nothing but so it means it is not known at each and every point within the domain. It is known at certain discrete locations. Why it is known at certain discrete locations? Because the process of converting partial differential equations into algebraic set of equations utilizes the discrete locations to represent derivative terms in terms of algebraic difference equations. Okay, so that's why in this process where we are converting our partial differential equation into algebraic set of equation, we need to first convert our domain into large number of discrete locations, then only we can actually apply or we can do the process of discretization. Okay, so for example, if you consider, say, this is your rectangular domain. So what we do in case of numerical simulations, first we divide this rectangular domain into large number of small locations. Okay, and say if I am talking about vertex centered approach, so in that case what will be happening? All these points will be acting as the discrete locations at which actually we are writing the algebraic difference equations, and we will be able to store data at each and every location which are indicated by these points. Is this point clear? Okay, so this process of discretization which converts your partial differential equations into algebraic set of equations, this will be only working if in our domain we have defined some discrete set of locations at which our field variables will be solved, and the differential equation will be written in form of algebraic equations for each and every of this discrete locations. Okay, and these discrete locations are nothing but called as your nodes. Is this point clear? So this process, whenever it is applied on a geometry, the process of dividing your physical domain into number of small elements is something which is called as meshing. Okay, so you also need to do meshing, because if you don't do meshing, then you cannot be able to convert your partial differential equation into algebraic set of equations. Okay, is this point clear? So this is the reason that whatever the solution we get out of this computational method, this is known only at these points. If I need to calculate in between these points, then I need to do interpolation. Okay, so that is the reason we say that numerical solution gives us nothing but the discrete solution. It's not a continuous solution. Okay, is this point clear? Now, one important part is whenever you solve a partial differential equation, okay, if you solve a partial differential equation, the solution of that, analytical solution of that partial differential equation will always be considered as the exact solution. Okay. On the other hand, if you numerically solve a partial differential equation, whenever you do this process of discretization, whenever you replace the derivative terms with algebraic difference equations, okay, the way I was discussing, say, in one of the lecture when we were talking about vorticity, for example, if you have to write dy by dx using the forward difference scheme at point I, then you will be writing a y at point I plus 1 minus y at point I divided by delta x plus order of accuracy will be delta x. Okay. So, what is the meaning of order of accuracy? The meaning of order of accuracy is whenever you have written this derivative term into this algebraic form, only this much was not your equation. Okay. In your equation, there were some other higher order terms also. But you have neglected these higher order terms because you cannot take these higher order terms will be extending up to infinity. You cannot take infinite number of terms into your solution. Okay, so you have to remove some terms which have smaller value. So once you are removing these terms, so your actual derivative term would have been this entire equation. But now you are writing actual derivative term only up to this point. So it means that you are removing this term. So once this term is removed, it will be introducing some error into your solution. So that type of error is called as truncation error. Okay. So always in your numerical solution there will be error. Now the delta x order will be depending upon the size between these 2 points whatever we have actually created. So it means that in your numerical solution, if you keep on decreasing the size, your truncation error will keep on decreasing. Okay. So that is the reason when you do the CFD simulation, what we say something called as grid sensitivity test, okay, or grid independence test. Okay. The meaning is for large grid size, error will be more, truncation error will be more, but when you decrease the size, the magnitude of truncation error will decrease, so you will get more accurate solution. Okay, but after certain amount of time, it may happen that round off error takes over the truncation error. Okay, after that point, you may find again the amplification in the error. So that's why some trade-off we make. Okay, so let's not go into that detail, but the major interest is that whatever the solution we are getting from CFD, that is not exact solution, that is a approximate solution. Okay, because we have approximated these differential terms we have approximated with some, yes, with algebraic equations which are not exact, which are already having some truncation error. Okay, so that's why we will always be getting the approximate solution, and a way to decrease the error in this approximate solution is something which we do in terms of grid independence test. Okay, so we try to see the effect of grid size on our output, and the point at which we see that after decreasing that size, our changes in the output are not much. Okay, so these changes are within the acceptable limits, so we will be considering that okay, with that grid we can carry forward our solution. Okay. So this is the process of CFD. Now, after understanding the process of CFD, let's talk about approaches of CFD. What are the different approaches which we can use for CFD? So if you see the different approaches which one can use, first approach can be you can write your own computer codes, okay, which can do all these processes what you have specified. Second approach is commercial softwares, and third approach is open source softwares. Okay. So whenever people do CFD, majority of the people, what they do, they write their own codes. Okay, and typically, whenever the field of CFD was evolving, of course, initially people have started with writing their own codes. But later on, some of the codes have become so robust that these have been commercialized for majority of the generic phenomenon, and then the evolution of commercial CFD softwares has taken place. Nowadays, we see the name of many popular CFD softwares. For example, one popular name is ANSYS. For fluid flow problems, there is one solver ANSYS Fluent, other solver is ANSYS CFX. Then say many solvers are there. Star CCM is there, Converge CFD is there. So plenty of the commercial softwares are nowadays available. Okay. So COMSOL Multiphysics is there. So many commercial softwares are actually available nowadays. So the point is, in terms of commercial softwares, they don't give you access to the source code. Okay, so you don't get source code from this. So what is source code? Typically, the code which is doing all these mathematical computations and discretizations at the back end, that is the actually main source code of the entire CFD software. Okay, but what they do, they provide you some graphical interface, and with the help of that graphical interface you can select different options, and based on these options it will be doing the computations at the back end, but it will not give you the access to the source code. Okay, so what computation it is doing at the back end, that will be, if you don't know the theory of CFD, then it will be looking like a black box to you. Okay, so that is something which happens with commercial softwares. However, commercial softwares at present are so much developed that majority of the phenomenon which you can think of can be solved using these softwares. Majority of the things are already implemented in this. Okay, but and moreover, small, if you have to do very minor modifications into the governing equations to include some terms or to do tweaking of some terms, then you can use some user defined functions. You can use some user defined functions also to do very small changes or minute changes in the physics of the problem as per your requirements. Okay, so it will not allow you to change the entire source code, but small tweaking into the say small inclusion of some extra terms can be done by using user defined functions. Then first category, of course, first category will be always you have the entire source code, because if you have written your entire code. And typically first category people uses when they are say introducing some new physics into the code. Okay, so majority of the time say some new physics if you want to add, then people have their own codes. So these own codes they can actually include in their earlier existing codes as well, or majority of the time whatever the small piece of code they are writing, then they can integrate these to even open source software. So how it can be integrated to open source softwares? Open source software are also nowadays plenty available. Okay, and one of the very popular for fluid flow and heat transfer problems is actually open form. Then there are many others also. For example, for multi-phase flow problems, Jeris is one solver, then Basilisk is one solver. Okay, then for particle simulations, LAMPS is one solver. So a large number of multi-phase flow solvers are also nowadays available. Again, Enura 3D. So there are so many solvers available. Okay. So the benefit with open source softwares is that these will be giving you access to the entire source code. Okay. So it means that if open source software is designed for some set of problems, if you want to say increase or improve the application of that software by introducing some extra physics, so you can do that and you can do implementations in that code itself because you have the access to the source code. But before doing that, you should have knowledge of the source code, the structure of the source code in which it is written, because then only you will be able to do changes in that. Okay, so these are the different approaches which typically people uses for multi-phase flow problems. And also computational community is of two types. One community is who develop uh, whose task is always to improve the existing solvers. So existing solvers can be improved by designing some higher order discretization techniques which can reduce the amount of error. It means which can give same level of accuracy at coarser mesh in comparison to go for a very fine mesh. So that will be improving the computational efficiency of the simulations. Okay. And some people who are trying to include some new physics which are not accounted for into the softwares or solvers yet. Okay. And second type of community is those who uses the computational tools to solve the physical problems of interest. Okay, so first type of community will only be using the benchmarking cases. Their interest is not to study the physical phenomenon, but majority of the time interest is to develop the methods. Okay, and the second type of community, those who have interest to study the physical phenomenon, they will try to utilize the softwares to solve their physical problems and then understand the dynamics of the physical systems. Okay. Now comes again one important part. Whenever we say that we are dividing this domain into a small number of discrete points, so always when we talk about CFD, one thing comes to our mind that always we have to actually use some grid kind of arrangement to do our simulations. Okay, but in actual practice, CFD is a simple term which is utilizing the computers to solve equations. It means discretization has to be done, but it does not tell that discretization can be done by only using the grid. You can also have some other methods to do discretization. So other method to do discretization is, if this is your domain, you can also divide this domain into large number of particles. Okay, rather than using grids, you can represent the fluid medium in terms of a group of large number of particles. So whenever we use this type of approach, then we call majorly the CFD methods as particle based methods. Okay, so the way we are utilizing our grid, in the similar way we can also utilize particles. So methods can be based on the grid based approach, or methods can also be based on the particle based approach, where your entire fluid is actually divided into large number of particles and then we are solving the behavior of these particles. Okay, so how to decide that whether to use particle approach or fluid approach, that is something which we can answer with the help of this master curve, where we have to decide that what is our scale of simulation and what are the length and time scales in which we are dealing with. Okay, so if our length and time scales are in the range of millimeters to close to of the order of micrometers, meters to micrometers, and time scales are in the range of milliseconds to minutes or few hours, then we are talking about physical phenomenon at macroscopic level. Okay, and once we are talking about the physical phenomenon at macroscopic level, our value of Nansen number will be very small for all these cases. So if value of Nansen number is very small, in this range we can apply continuum mechanics. Once we apply continuum mechanics, then all the grid based approaches will be actually working fine. Okay, and the majority so popular methods for grid based approaches are finite volume discretization, finite element discretization, or finite difference discretization. Okay, then comes the second approach, when your sizes has become of the order of few nanometers to some micrometers and your time scale is in the range of microseconds to milliseconds. In that case, you will be finding that your criteria of continuum may not be applicable. So once criteria of continuum is not working, you cannot treat your fluid medium to be a continuous medium. So what you need to do, you need to divide the fluid medium into some discrete particles, because when you are not considering a fluid medium as a perfect continuum, then what will be happening? There can be voids in between the containers or in between the systems where actually fluids are placed. So I am not saying that continuum is completely vanishing in this case. This is just a bridge in between the no continuum to the pure continuum. Okay, so the bridge in between the no continuum means where you have to account for individual molecular motions. You cannot treat a group of molecule as a whole. You have to consider the behavior of each and every molecule. So in between that approach and the pure continuum approach, you have some bridge. So that bridge can be dealt with mesoscopic modeling, where what you can do, a group of molecules can be clustered together and can be described as some artificial particle. Okay, and combination of large number of particles will be forming your entire fluid medium. Is this one clear? So combination of large number of particles will form your entire fluid medium. So this type of methods are majorly particle based methods. Few methods are having their grid approach also. For example, in case of lattice-Boltzmann method, there is grid, but there are preferential directions in which the property will be transferring. Okay, so these methods are typically smoothed particle hydrodynamics, dissipative particle hydrodynamics, and lattice-Boltzmann methods, etc. And when you go below further, your sizes go below further, for example, in the range of nanometers or angstrom, and time scales are in the range of say picoseconds to nanoseconds, there what will be happening, your system is so small, okay, size of the system is say 1 nanometer or 2 nanometer. So in that scenario, you have to study the behavior of individual molecules. Okay, so there we go for the molecular dynamic simulations, and in terms of molecular dynamic simulations, there can be coarse-grained molecular dynamic simulation where you are looking the behavior of all molecules, and some atomistic simulations also where you are interested in the fluctuation of charges within the atom itself. Okay, and if you go even below that, say somewhere close to femtosecond, 10 to the power minus second, 16 second, then comes quantum mechanics, and you have to use some methods. These are nothing but the methods which are used for the motion of the quantum particles. Okay, so that is the overall spectrum. But in our course, because we are talking about engineering approach, in engineering approach majority of the time we are in this category. So our length and time scales are such that all our physical phenomenon can satisfy the continuum. Okay, but typically this is something which works when we are talking about single phase flows. But when we talk about multi-phase flows, then even in our larger scale also there can be some scenarios where we have to account for the microscopic effects in our continuum models as well with the help of some ad hoc modeling approaches. Why? Say I have some system in which two interfaces are coming close to each other. Okay, so this is also coming close to each other. So what will be happening? At some point of time, you may find, if I zoom in into this portion, you may find that this is one interface, this is other interface. And between these two interfaces, say, the gap is of the order of nanometers. Then what is happening? In this nanometer gap now, molecular motions will become important. Okay, so you have to, though you are solving this system using continuum approach only, okay, but whatever the effect these individual molecules will be causing in this very thin zone, you have to account for certain forces. Okay, so how these forces can be accounted for? So you can add some source term in your equations to account for the additional forces because of the molecular effects. Okay, so that's why whenever we solve the multi-phase flow problems, majority of the time when we are looking at gross parameters, we need not to look into such microscopic details, but say when we are looking into the microscopic perspective, say two bubbles are coming to each other and then joining and forming a big bubble. Okay, so there will be some fraction of time scale in which the distance between the two bubbles will be maybe of the order of nanometers. Okay, and during that time interval there can be some molecular effects important. So that's why when we deal with the interface, then things become bit more challenging. Okay, now let's talk about when we have the multi-phase flow modeling, then what type of approaches actually we can use. So first approach is Euler methods or Euler approach. Okay. Second is Euler Legrange approach. And third is DNS of multi-phase flow. So these are the three popular methods. First approach is Euler approach. So Euler approach is identical to our separated flow models. Okay. What we were doing in case of separated flow models? Fluid 1 we were solving separate continuity momentum equation. Fluid 2 we were solving separate continuity and momentum equations. And then we were using some interaction forces to couple the boundary effects between the two fluids. Okay. So that type of approach when we use, that is called as Euler methods. And Euler methods majorly we use when both the phases are nothing but fluids. If one of the phase is a particle, then we don't use Euler approach. And majority of the time, when both the phases are actually continuous, then also we can go for this approach. Okay. Second approach is Euler Legrange approach. So in case of Euler Legrange approach, what we do, continuous phase will be modeled using Euler approach and particles will be modeled using Legrange approach. So for continuous phase we will be having continuity and momentum equation, and for particles we will be having discrete particles, okay, And for particle also we have to write its equation of motion. And what will be the equation of motion for a particle? Earlier I have given you brief idea. In detail, if time permits, we will then see. So if you recall, in one of the lecture I gave you one equation, mass of particle into dV by dt equal to drag force, lift force, then there were some history force, there were some added mass force. Okay, so all these forces we have to actually account for. And these forces, so some of these forces such as drag and lift, these will be coming through the interface between the fluid and the continuous fluid and the particle. Okay, so these forces are coming because of the fluid. So of course particle will also impose certain forces on the fluid in the opposite direction. So then in between particle equation and the fluid equation we will be having some coupling through interactive force systems. Okay, and third approach is called as DNS for multi-phase flows. Now when we talk about the DNS, from our turbulence understanding, we know that DNS is nothing but direct numerical simulations, and the meaning is if we are able to resolve the finest length scale of the turbulent eddy and fastest time scale of the turbulent eddy, then we call DNS for turbulence. But here the term DNS is slightly different. It is taken in same context, but the nature of the time and length scales is slightly different. Here, what we want to consider that for multi-phase flows, if we are able to capture the smallest to smallest interface fluctuation and fastest interface evolution, then we call that as nothing but DNS of multi-phase flow. Is this point clear? So when we are using the DNS term, if I say that I am doing DNS for multi-phase flow, it does not mean that my grid is resolving Kolmogorov length and Kolmogorov time scales, which are considered as the smallest length and fastest time scales in turbulent eddies. It does not mean that I am resolving up to that level, but I am resolving up to the level where my interface can be resolved properly. Whatever the shape deformation is taking place in the interface, that can be properly resolved using the grid structure, and that can also be, if it is evolving with time, then also it can be captured. So once I am able to capture in that sense, then I will be calling that I am doing DNS for multi-phase flow. But be careful, don't mix it with the DNS for turbulent flow. Okay, because there the length and time scales, grid size and time step size will be even more smaller. Is this point clear? So in case of DNS for multi-phase flows, we will be able to properly resolve the interface. Is this one clear? So now let me give you quick examples. So see this first video. This yellow colored thing, so this is volume fraction of air. So yellow color alpha equal to 1 means it is representing pure air, and pure blue color over here is representing pure water. Okay, now I have to select pointer arrow. Can you see this? So here if you see, volume fraction of the fluids is actually changing. Is this one clear? In the top you can see this amount of air is decreasing and amount of water is increasing. Okay, and in the center also you can see patches, different patches of volume fraction. So this you can consider, this is nothing but a bubble column reactor in which a plume of bubbles is actually purged through the water. Okay, so when a plume of bubbles is purged through the water, here our interest is not to calculate how many number of bubbles are going, what is their size, how their shape is changing, but our interest is in determining what are the zones where volume fraction of bubbles is more and what are the zones where volume fraction of other fluid is, water is more, where volume fraction of bubble is more. So when our interest is of that type, then we apply the models which are called as Euler models. Okay, so in case of Euler models, along with solving the separate continuity and momentum equations, we are also solving the volume fraction equations. Okay, we are also determining volume fraction of the phases. Okay, but we are not resolving the system to the finest level so that I can track the interface. That is not my interest. My interest is only to determine the interfacial interactions, and because of these interfacial interactions where fluid 1 is present and where fluid 2 is present. Only if I have to determine that type of zones, if I have to only determine what is my void fraction within this tube, then I will be going for Euler models. Okay, I will be considering the two mediums to be continuous only, and then I will be simply seeing where volume fraction of one medium is high, where volume fraction of other medium is high. Okay, then comes, this is DNS approach. Okay, so in case of DNS approach, what will be happening? So for DNS there are multiple methods, one by one we will see in the subsequent discussion, but in terms of DNS approach we will be finding that, here you see, so this blue colored thing is water and yellow colored thing is air. So this is an air bubble which is rising in water. So now I am considering my grid size in such a way so that I am precisely able to calculate the evolution of the interface, changes in its shape and how it is behaving with space and time. Okay. So when I am resolving up to that level, then I will be calling this as DNS of multiphase flow. Okay, and of course for doing DNS there are again many methods. So what are these methods that I will discuss? So popular methods are, say, volume of fluid method or level set method. So what are these that I will discuss in the subsequent discussion. Okay, is this one clear? So in case of DNS approach, our interest was to look into the interface evolution. So we are resolving grid up to the scale so that my interface can be tracked properly. Once again you can see, so this is an initial spherical bubble, then you can see its volume is large, because of which it is deforming, becoming elliptical, and then actually it is rising in the tube. So before the time it has become completely elliptical, it will be having changes in its velocity. Once it has become elliptical and there is no further interface deformation, then it will be achieving its terminal velocity and it will be moving with the constant velocity. Okay, is this one clear? Then the next approach, what was the next approach? Euler Legrange approach. So in case of Euler Legrange approach, our interest is, this is applicable when we are having particle type multiphase flows. For example, gas solid flows, liquid solid flows, etc. Okay, so in this type of system, what we are doing, even if you have, say, some small very fine size spray of bubbles or drops, then also you can use the Euler Legrange approach. In that case you have to just make one assumption that bubbles or drops are not deforming and these are not breaking into new entities. So then you can actually approximate these bubbles and drops also with the help of some solid particles, and you can solve these using the Euler Legrange approach. Okay. So in this approach, the fluid, because I told you that either we can have gas solid or we can have liquid solid flows. Okay. So there will be two fluids, one will be dispersed phase, which is a particle phase, and other will be continuous phase. So continuous phase is modeled using the Eulerian approach, and discrete phase is modeled using the particle approach. And of course, for particles we will be having equation of motion, as I told you previously. So here you can see this is the simulation of a cyclone separator. So in a cyclone separator, how particles are flowing. So you can see tangentially a mixture of gas and particle enters in a cyclone separator. Mixture enters tangentially, then the particles, because of their heavy size, they move in the outer periphery and particles settle down at the bottom, and through this center outlet only gas will be going out. Is this point clear? So that is something which is shown over here. And typically when we apply the Euler Lagrange model, we don't consider particle-particle interactions. Okay. For few cases, for majority of the cases, particle-particle interactions are not considered. What are the standard Euler Lagrange models available in your some of the CFD codes? Okay, so it means that in that case you can only apply the Euler Lagrange model when your particle concentration is small. If your particle concentration is large, then in your physical system, particle-particle interactions will become strong. Okay. So if you are not able to resolve up to that level, that what is the effect of particle shape, because here when we are considering the Euler Lagrange approach, we are considering that our particles are of spherical shape only. Okay. But in real practice, if you have to resolve at the very finest level of the particle size, then particle shape can be arbitrary. And when particles, then the effect of particle orientation has also to be accounted for. Okay, then the effect of particle interactions has to be also accounted for. So that is something which is not included in the Euler Lagrange model. So that's why Euler Lagrange models are mostly applied when concentration of the particles are actually small in the gaseous medium. Typically the safest range is less than 10%, but many times even up to the concentration of 30 to 40% also Euler Lagrange model can be applied with good accuracy depending upon the nature of the problem. But of course, if more than that we are going, then we cannot use the Euler Lagrange model. Then we have to go for the models which can resolve the particle-particle interaction, and the models which can take care of the particles orientation, and the models which can take care of the particle fracture when two particles will be collapsing with each other, then there can be fracture of the particles. Okay, so these type of models particularly comes under the category of discrete element methods. So discrete element methods are popularly used by the say civil engineering community or solid mechanics people to discuss the particle effect of particle orientations and the particle-particle interactions. Okay, so for non-spherical particles. So for our understanding of fluid dynamics, we are considering the slurry transport, we are considering the gas-solid flows. Here we are assuming that particles are of spherical shape when we are using the Euler Lagrange approach. Is this point clear? So this is some introductory idea about numerical simulations and majorly what are the common approaches for solving multi-phase flow problems. Okay. Now we will not discuss much about Euler problems. We will first discuss about the DNS of multi-phase flows. So when we discuss about the DNS of multi-phase flow, because we have to resolve the interface, so we have to see different mathematical possibilities with the help of which I can define the location of the interface, and that location of the interface I can track how it is actually evolving with time. So that is something which we will discuss from the next lecture onwards. And after discussing DNS of multiphase flows, if some time permits, then we will quickly recapitulate this IER Legrange model also in one lecture. Okay.